Okay, so I have started the recording and I will turn things over to Elizabeth Cochran in just a second. Just like to welcome everyone to the Monday seminar. I am thrilled that we've been doing this as long as we have been, thanks to the kindness of people like Elizabeth who've put together a talk and are prepared to give it to us by Zoom at 7 o'clock in the morning for her. Sorry about that, Elizabeth. This seminar series started 5 years ago, out of the time when we were all locked down. And then, I don't know, over the years, yeah, it's just, we've realized that it's an incredible opportunity. And it's something that we can do in the context of our regular day. So here we are. Wonderful to see you. I recommend to you, our normal mode of operation is to ask people to mute themselves in the background. But normally it's okay to, we encourage you to participate. So if you've got some point of clarification or a small question along the way, I'm sure Elizabeth would be happy to be interrupted to make herself feel less like she's just talking to her screen. And then, yeah, we really want to encourage everyone, and especially young scientists, young people early career people, to participate in the discussion at the end. Don't wait. The discussion at the end is not just for some idea of some experts. It's for everyone. So write down your question and be prepared to interact. Normally there's a nice opportunity to have a discussion and hear more things from Elizabeth, ask questions at the end. So without anything more, I will turn things over to Elizabeth and thank her for being here.
Thanks, Chris. Thanks for having me, inviting me to this seminar series. I unfortunately have not attended too many in the past because of the time, but I am happy to be here today. So today I'm going to talk about sort of a tour of some observational and modeling studies that we've done to understand wastewater disposal-induced earthquakes. I got my start in this field soon after I joined the USGS. So I joined the USGS in sort of June of 2011, and a few months later, the Prague, Oklahoma magnitude 5.7 earthquake occurred. And that sort of, I went out and installed some stations there and studied that sequence. And of course, the earthquakes continue to happen in Oklahoma and Kansas, and now in other places. And so I've been studying them ever since. All right, so this is just showing a plot from Langenbroek and Zoback, looking at the number of number of earthquakes in Oklahoma. So here's Oklahoma. The dots are the earthquakes, and this is just showing the rate of earthquakes since 1980, and the real departure from that kind of traditional curve starting around 2010, and the 2011 magnitude 5.7 Prague earthquake occurred right about here. So, we're looking at a dramatic increase in the seismic hazard from these events that continued for about a decade and still continues today, although at a lesser level. All right, so as we started studying these earthquakes, the question is what's causing them? If we look at oil production here in blue, we can see that the oil production increases kind of correlated with our increase in the number of earthquakes. But we all know that correlation does not equal causation. And if we look back in time, we can see back in the 1980s, oil production was the same or perhaps a bit higher than during the kind of peak time of injection-induced earthquakes. So through a number of studies, looking at kind of what is the difference between what was happening in oil production back in the 80s compared to more recently. Essentially, the large difference is the amount of wastewater that's produced along with oil that has to be disposed of. And so that is re-injected underground. In the case of Oklahoma, it's re-injected in in a formation that's closer to basement than the production and was actually an area that was previously produced in the 1980s. So we're kind of refilling this deep reservoir right next to the basement. So that's what's loosely shown here. We have, this is just a schematic showing that we can produce oil out of shallower layers, and then the injection happening in the Arbuckle is at deeper layers close to the basement rocks where we might expect to be able to host larger earthquakes. So that's kind of the basic idea. We see that quite nicely if we look at the, so this is again from that Langenbroek and Zoback paper. Again, if we look at the wastewater injected, and in fact look at the pressure, expected pressure from that wastewater injection, you get a really nice correlation with the earthquake rates. And so, on a broad scale, we understand what's causing these earthquakes in that are happening in Oklahoma, Kansas, and other parts of the US. So, a lot of that focused on this area in Oklahoma, which had a lot of earthquakes and the peak earthquake rates in 2015. More recently, we've seen increases in Texas, in the Permian Basin and the Eagle Ford Shale. So those, and this plot isn't continue to be updated, but the rates are continuing to increase here in Texas. So we've had a few magnitude 5s now in West Texas over the last few years. But there's some sort of more detailed questions that we want to better understand. And so I'm going to walk through a few different questions that I'm going to tackle during this talk. So the first question is, are induced earthquake sequences any different from natural earthquake sequences? So early on, there were some statistical studies by Lanos and Michael that showed that induced earthquake sequences did seem to have different statistical properties than tectonic earthquake sequences. Basically, the way that the earthquakes were triggered and the number of aftershocks that they had kind of differed. But we'll look at that in a different way as well to see if we can see evidence for that in other ways. And then the other two other questions we're going to look at is, do only well-oriented fault structures fail? So when we think about looking at hazard from induced earthquakes, we want to be able to hopefully pick out, for example, which faults we think are most dangerous and perhaps avoid injecting near them. And so, a typical way of doing this is looking at the orientation of the fault within the sort of dominant stress field in an area. And then you might assume that the earthquakes that the faults that are well oriented within that stress field are going to perhaps be more likely to fail when you increase the pore pressure a little bit. So that's what this study by Walsh and Zoback is showing. It's just sort of mapping the likelihood of the faults that will fail or are more likely to fail, and the red being the more dangerous ones. And then a correlation or a correlated question we have to that is whether or not injection broadly will alter the stress orientations. So if your injection is somehow changing the stress orientations, you then have to maybe be concerned about a new set of faults becoming well-oriented in that stress field. So those are our seismological observations that we're going to look at using some data sets, and then I'm going to also discuss some modeling results that we have on a couple other questions. So the first is, does maximum magnitude always scale with injected volume? In general, if you look at induced earthquake sequences, the maximum injected event scales nicely with the cumulative volume injected. But there are cases where that's not true. So for example, the magnitude 5.5 Pohang, South Korea earthquake kind of fell outside of this expected relation. So we're going to use some modeling to kind of look at what conditions you might have in order to see something like that Pohang earthquake occur. And then finally, we're going to look at can we change how we inject the wastewater to reduce the induced earthquake rates or magnitudes. So there's an example in Paradox Valley, Colorado, where there's a deep injection well. It's a saline water injection to reduce the saline in the Colorado River. And they've had a number of induced events related to injection. And so they have put in place some changes in their operations to basically inject for a certain amount of time, and then they turn off the well in order to reduce the pressures, and then start up injection again, and hopefully the pore pressures have dissipated a bit, so the earthquake rates or magnitudes will be lower. All right, so let's jump in. So I'm going to take us first to southern Kansas. So this is this map up here is Kansas up here, Oklahoma just to the south. We'll be looking in this little area here. So as earthquake rates increased in Oklahoma, Justin Rubenstein realized that operators were moving into northern Oklahoma and southern Kansas to target the Mississippi Lime play. And so Justin got out there with a set of seismometers, the black triangles here, to try and record the expected uptick in seismicity, and did capture that, although seismicity had started already a bit before the array was fully in place. So this is showing Justin's detections of events across this area. The circles are scaled by magnitude. The inverted triangles here are the injection wells. And so you can see there's a lot of earthquakes occurring across this entire area. These included two somewhat larger events, the magnitude 4.6 Harper earthquake. And the largest event was a magnitude 4.9 Milan earthquake. And it is Milan, Kansas, not Milan. So what we did was we took this catalog and we did template matching on it using a match filter technique of Zach Ross's and based on David Shelley's methodologies. In this case, we're taking a 2-second window around the P and the S waves and using the previous event catalog to detect additional events. And so we end up getting these earthquake families with lots and lots of detections. I'm not calling them repeating earthquakes because I haven't gone through and done the detailed kind of relocation and confirming that the sources are overlapping. We actually have a postdoc who's working on that now. But this is just showing one of these families. There's 387 events within this family, or detections in this family, that match to a template event. You can see the waveforms are all quite similar, maybe some variations through time, but we see a number of these energetic families. All right, so this is looking at if we look at all of the events we detected through that template detection, we have lots of the original catalog events, which only have 1 or 2 additional detections, but we have a large number that have at least 100 detections or more. So I'm going to call these prolific families. I'm just making an arbitrary cut here and just selecting the families that have lots of events. I'm doing that so that I can do some additional analyses and look at kind of their evolution through time. So if we look at the distribution of these prolific families here, I've plotted each of our original templates and I colored the templates by the number of detections. with lighter colors meaning fewer detections and darker colors meaning more detections. And then I've outlined in blue these prolific families. So these are the families where we have at least 100 kind of events in these families. The base map here is just taking those injection wells and turning them into the total volume injected over this time period, which is about 4 years. So you can already see that the distribution of these prolific families it's sort of not the same everywhere. So we have a huge cluster of these prolific families just north of where we have most of our injection happening. And then we have others scattered in different places. So along the Mylon magnitude 4.9 earthquake sequence, we have a few, and then a few along other structures, but not a huge amount here in the south where we actually probably have some of the higher, or at least did have some of the higher pore fluid pressures, because a lot of the injection is also occurring south of the Oklahoma-Kansas border. All right, so already we're seeing the spatial distribution that's interesting. I've labeled 1, 2, and 3 here for 3 different families we're going to look at in a little more detail. So this is that first family, which we can see has events. This is looking at magnitude versus time. We can see that the distribution of events is fairly constant through time. So we have, looking at the sort of cumulative number of events through time, we see that it's sort of increasing at a steady pace. This is a log of the inner event time. So if we look at the time between two successive events, what is that time? That's shown by this distribution here. We can see that on average, if you were to figure this out, it's about once every 10 days that we're getting an event. This is that second event near number 1, or second family near family number 1. You can see in this case, we have initially kind of a cluster of events, and then they sort of tail off into more regular occurrence. That's also reflected in these inner event times where we have more clustered, shorter inner event times, and then this set of inner event times that's very similar to family 1. And then if we look at number 3, which is along that Mylon earthquake sequence, we have just a cluster of events and then very few events otherwise. So we're seeing quite different behavior depending on which event, which family we look at. We can go ahead and quantify this behavior. So Hagen and Jackson defined what's called a coefficient of variation of inter event times. This is simply looking at what's the standard deviation in your inter event time and dividing that by the average inter event time. You may not have kind of an intuitive feel for what that means. So if this was 0, so you have 0 standard deviation, then your events are entirely periodic. If it's around 1, this means your events are Poissonian distributed in time. So these are kind of independent events caused by steady forcing, so tectonic stress, or if you have a sort of steady increase in your stress due to nearby injection. And then as you go to higher values of this coefficient of variation of inter event times, you get to the kind of classic main shock aftershock sequence or swarm type behavior. All right, so we can look at, for all of these families, I'm plotting the cumulative number of events through time, just everything's normalized. And I've colored these lines. So each line is one family. I've colored the lines by their coefficient of variation of inter event times. So green, these are families where we have events happening very regularly, kind of this Poissonian distributed in time set of events. And then as we go to the blue and the purple pink color, these are our more clustered events. You can see most of these, the clustering takes place, or the rapid set of events takes place mostly early in the sequence, and then you might have a couple of events continuing but at a lower rate later on in the sequence. So you can see that we've got quite different behavior across these families. So we can look at the spatial distribution of the coefficient of variation to see if we see any interesting patterns. So again, the green ones here are those ones that are caused by maybe more Poissonian distributed in time, more constant stressing rates. You can see that these typically are, or almost all, occurring near our injection wells, so perhaps are being more directly driven by injection. And then we see farther away, we have a lot more kind of clustered main shock, aftershock type behavior. And our interpretation here is that, you know, maybe the initial events are triggered by the pore pressure passing through, but then pore pressure changes are lower. And so you're getting really a dominated behavior from the stress changes due to earthquakes that have occurred. And this is just highlighting again near these different sequences. Sequence 1, which is here. 2, you can see we get a little bit different behavior depending on the fault that the events are occurring on. This is more of a strike-slip fault. This is a normal fault. And then here we have the Mylon event, which is strike-slip. All right, so this is showing us that our earthquake sequence behavior can vary depending on space, where they are in space, and probably are depending on how close they are to these high rate injection wells. All right, so in some cases, we do see that these induced earthquake sequences might show some differing behavior from natural sequences, or at least on shorter spatial timescales than what we would typically see for tectonic events. All right, so we're going to move on to the second part of the observations, which is looking at kind of the stress field near faults. All right, so we all know kind of from rock mechanics that we would expect faults to fail at a certain orientation relative to the maximum compressive stress direction. And we see this quite commonly in rock physics experiments. And so if you take that into the field, if you know what the background stress orientation is in a particular area, so that's denoted here by these large arrows, you can estimate how likely it is for a fault to fail under different pressure conditions. So this has been used to develop a method of looking at fault failure potential in these areas of induced events. This particular fault strand here is the fault that failed in the magnitude 5.7 Prague earthquake. Again, Prague, not Prague. So you can see that in this case, the prediction was that this fault was quite well oriented to fail. And so they look at the probability of slip versus pore pressure perturbation. The faults in red are kind of well oriented and likely to fail. All right, so we did see that in the case of the main shock that the Prague earthquake occurred along a well-oriented fault. But we're going to take a closer look at this sequence. So again, this is the magnitude 5.7 Prague earthquake that happened in 2011. We again used catalog and a template matching to identify additional events along this sequence. So we're looking at the aftershock sequence here. And then I'm going to use the earthquakes along with a mapping of those earthquakes into faults called fault ID to map the sequence. All right, so just to give you a little background, the magnitude 5.7 main shock occurred on this fault here. It was actually preceded by a foreshock, a magnitude 5 foreshock oriented slightly more northerly than the main shock. And then there was also a magnitude 5 aftershock that was oriented basically east-west. So we have a number of fault orientations just represented by the three main events in this sequence. We're going to estimate the stress, the background sort of local stress using shear wave splitting. This is a technique where you look at the incoming shear waves, and if these shear waves are traveling through a rock that has cracks in it, in particular aligned cracks, which is typical because the cracks will typically align with the regional stress field. So if you have an SH max in this direction, your cracks will tend to orient parallel to that maximum stress direction. So we can actually measure this in the shear waves. And we did this using the local station distribution and looking at the local shear wave splitting. So these green lines here are our estimated maximum compressive stress direction, with the dashed lines indicate kind of the error on those. And you can see that across much of this fault plane, we have very similar stress directions, and this is actually similar to what was shown in that previous plot looking at the fault slip potential. We also map our earthquakes into fault. These are these thick straight lines. So the foreshock fault plane, main shock, aftershock, and then a bunch of little ones that are maybe more difficult to see. We've colored these from deviation from the optimal orientation based on the kind of closest stress shear wave splitting stress measurements. So yellow means it's well oriented. Red and especially dark red to black mean that the fault is not well oriented. So our assessment here is that both the foreshock and the aftershock are probably not very well oriented in this local stress regime, and likely were triggered by probably the foreshock. Most of the injection was happening up here in the north, and we're thinking maybe the very high pore pressures developed along this fault plane that triggered the foreshock and then the main shock, and then the aftershock kind of remains a mystery. A number of folks have looked at it, and both in terms of Coulomb stress as well as orientation, fault orientation in the stress field. It's a mystery why this one ruptured. So still things to figure out. So the second part of this is looking at whether the injection can broadly alter the stress orientations in a particular area. The study that we did was kind of motivated by a study by Nolte et al. In 2017 that reported in southern Kansas, again, we're going back to Kansas now, a 75 to 150 degree rotation in the maximum compressive stress in southern Kansas. So they measured this in the same way that we measured the stress near the Prague earthquake by looking at shear wave splitting and isotropy. And so in this study, they took different sets of instruments and looked at what the shear wave splitting was across southern Kansas, and note that there is a large change in this is the delay time, but also note a large change in the maximum compressive stress direction through time. So we, Rob Skumal and I, decided to look at this in more detail. Rob had been looking at stress orientations across Oklahoma using both focal mechanism inversions as well as borehole breakouts and shear wave splitting. And we extended this into southern Kansas, again, using that nice set of stations that Justin had installed prior to most of the seismicity. So, yeah, we're going to take these different measurements. They're all listed here. SWS is shear wave splitting. So the red and the blue are shear wave splitting measurements in here. And then we have focal mechanism inversion in the magenta color. And we have Oh, is there a
מה נשמע
question?
אצלך?
Oh, I think.
באת לנוח?
I think we need muting. Okay. So there's also drilling induced tensile fractures in black and estimates from the fault orientations. So we took a look at, this is the earthquake rate at the top, the number of shear wave splitting measurements that we have through time, and looking at both the delay time and the fault, the fast direction or the maximum compressive stress direction. And you can see that both measures of this, we don't see any strong change in the fast direction or the delay time during this period. We think the difference here is that we were using a very consistent set of stations. Shear wave splitting can be very dependent on your source station orientation. And if you don't have a good set of stations around the area where you're looking, you can get kind of misestimates of what the true stress direction is. So anyway, we're not seeing any large changes in stress direction, and we perhaps wouldn't expect it. We might be more likely to expect that, if anything, the delay time would change. So as you open up the cracks, perhaps as your pore pressures get higher, you might see that effect. However, in this case, we're talking about changing the pressures within a fairly narrow reservoir. And we're measuring the shear wave splitting delay times over the entire path. And maybe shear wave splitting can be more dominantly affected by near surface. So
quick question,
yeah.
Ms. Chris.
Yes.
The events that you're looking at here are teleseismic or they're local?
No, these are all local. They're all
Okay, so
local events.
local measurements that are recorded locally. That's the
Yes,
thing.
correct. Yeah, so it's not, so you can do shear wave splitting measurements from teleseismic events. Typically for that, you would be more interested in looking at the anisotropy in the lower crust or mantle. So in this case, if we want just the crust, we use local measurements. Yeah.
Thanks.
Good question. Thanks. All right, so we've gone through our seismological observations. We just to recap, we don't see a significant rotation in our maximum compressive stress direction. And we have found that at least in some sequences, we can have both optimally oriented and poorly oriented faults fail in these areas of induced earthquakes. All right, so we're going to move on to modeling. And the first thing we're going to tackle is kind of one of the primary questions in induced seismicity, estimating what the maximum magnitude is. Obviously, the seismic hazard is highly driven by what the largest earthquake is that you can expect. And so it's a critical question to understanding what the risks are from induced seismicity. And as I mentioned, there have been a number of studies that have looked at this in various ways. We're going to take a slightly different approach and use a simple model of a fault. All right, and as our wastewater injection decreases, you might wonder if we still need to worry about this. Well, as we're looking towards carbon sequestration, we have a lot of the same concerns in terms of changing the pore fluid pressures in the subsurface as we're sequestering carbon underground. And so kind of the volumes of CO2 equivalent that might need to be stored underground are kind of on the same order of the wastewater that has been injected into Oklahoma and Kansas. So it kind of remains a concern, or is a concern, as we look towards carbon sequestration. All right, so this is a study from Art McGarr looking at the expected moment versus injected volume. A number of you are probably very familiar with this. Essentially, what this says is that as you increase your volume, your maximum magnitude is expected to grow. basically the idea behind this is as you inject more fluids, the larger the fault length is that's affected. And so therefore, if the size of your earthquake is dictated by kind of how much you've changed or how much of the fault you've changed, you've increased the fluid pressure along, you would expect that increased volume will kind of scale and give you an increased maximum magnitude. There's another way of looking at this. Nicholas van der Elst and did a study looking at from a statistical sense, as you change the stresses, you're going to increase the number of events, but then you're going to draw the magnitude, the maximum magnitude from your Gutenberg-Richter distribution. So yes, on average, you would expect that as your injected volume increases, the number of events you have increases, and therefore the probability that you will get a larger event also increases. But that's not to say that you couldn't get unlucky and draw from that Gutenberg-Richter distribution a larger magnitude event, even if you have a small total injected volume. So, there have been a lot of studies that look at this, and in general, a lot of observations do kind of match this volume injected scaling with or the maximum magnitude scaling with the volume injected. There are some cases that don't. This may include the magnitude 4.9 Milon earthquake. Also, the magnitude 5.7 Prague earthquake was kind of right on the edge of this relationship as well. All right, so we're going to do a really simple set of models to look at this question. These were led by Kayla, who's going to give a talk later in this series, but she's going to talk more about a tool to estimate kind of what the expected sequences are that you might see. All right, so we're going to use RSQ Sim. So this is an earthquake simulator that's based on rate and state friction. And again, we're going to start with a really simple model. So we're going to inject into confined regions along one fault. So we have one well, one fault, and we are going to only inject and not allow pore pressure to propagate outside of these little boxes. And we're going to basically run this model a number of times over these different size confined injection regions. The reason that we wanted to confine the pore pressures within these boxes is to allow us to look at kind of, okay, if we've only pressurized this section of the fault, do we ever get ruptures that go outside of this region? And of course, your ability to rupture across a fault depends strongly on the stresses that you have. So we tested models with both homogeneous and heterogeneous stresses. So we did a set of models where we had the background stress across the fault was homogeneous. And then a number where we did different distributions of the stress. Ones where the stress was highly heterogeneous and very small scale. So you can see the little speckles here, hopefully. And then other versions where we had kind of these larger scale, higher, low stress blobs across the fault. And superimposed in that is our confined injection regions. And so we wanted to see what happened as we inject into these regions and across these different stress regimes. All right, so this is a summary of the results. So here, the top left plot is maximum magnitude. We tried a number of different initial stress values here. And in this case, we're just looking at the homogeneous stress cases. So as you might guess, as we have higher stresses across our fault, we're more likely to just get an end-to-end rupture across that fault, right? Any event, it's going to be very easy for it to propagate across the entire fault. And this is kind of regardless of the size of the pressurized zone that we have. But as we go to lower stress cases, you can see that in general, we have the size of the maximum magnitude kind of scaling with our pressurized zone. So this smaller pressurized zone has lower maximum magnitude. And similarly for the slip, we have lower slip in those cases where we have a small pressurized zone. And this is just looking at the total moment across all of the events that we have in the sequence. I should note that RSQSIM allows you to do sequences of events. So this is looking across a large cycle of events across this fault. All right, so then if we look at, that was a homogeneous case. If we look at all of the cases that we ran, the homogeneous fault cases are in these solid filled in circles. And then the heterogeneous cases are in the open symbols here. And what I've done here is basically we've recreated that plot of looking at volume. Not in this case, it's not volume injected. It's the size of the pressurized area versus the maximum magnitude of the events. And you can see that in general, we have many cases where our earthquake is really constrained to be within that pressurized region. However, we do have these cases which are kind of runaway ruptures. You'll notice on the heterogeneous cases where we have runaway rupture, this is again where we have higher initial stresses. And if we look at the stress distribution, we typically have to get runaway rupture, we need long wavelength, low amplitude topography stress fields across the fault. So it's more analogous to the homogeneous case. And this is likely because if you have lots of stress heterogeneity, you're going to have smaller ruptures, and also that stress heterogeneity acts to impede those ruptures. The other thing, this last point, I think is an important one. We find that these runaway ruptures tend to occur early after we start injection. So these aren't, we keep injecting for a long time and then eventually we get a runaway rupture. These tend to happen early after we start injection and with quite few foreshocks. And this is sort of counter to a number of studies that methods that are proposed for controlling induced seismicity that say that you can look at the foreshocks, or you can look at the small events and see as those magnitudes grow and decide, okay, those earthquakes are getting too large, we should reduce our injection. So in these nice, well-behaved cases, that's true. That is what we see, but it's not true for the case where we get runaway rupture early, regardless of kind of the total size of the pressurized area. So this is just saying the background stress on your fault really matters. And that's a problem because we currently don't have a way of estimating what the background stresses are across our faults. Okay, and then in the last few minutes, I'm going to talk about our most recent work, again, using RSQSIM and looking at if we change our injection schedule or injection rates through time, how does that impact our earthquakes that occur? All right, so this, as I mentioned towards the beginning of the talk, there are some operations that basically have cyclic injection. They inject for a period of time and then they turn off injection to allow the pore pressures to dissipate, and then they restart injection. So we're going to do this kind of thinking about the carbon sequestration case where maybe you want to inject a certain volume of CO2 or wastewater into the subsurface within a certain time period. And we're going to take a pretty long time period. I think we're looking at something like 70 years or something. but we're going to change whether we inject constantly over that time period or whether we vary, turn on and off injection, but again, keeping the total volume over that long time period the same. And so this is our setup. So we have two cases. We have this constant injection over 70 years, and then we take that same volume and instead we inject it over bursts of time. So we inject for 10 years, and then we stop for 10 years, and we inject for 10 years, and we sort of turn it on and off. And we do this because the initial stress matters so much. We use 500 different initial stress realizations with two average initial stress values, kind of a higher average value across the fault and a lower value, and then these two injection schemes. Already, if we look at the overpressure that we estimate on kind of the closest fault element, you can see that on the constant injection, we get a steady increase in our overpressure through time until we turn off the injection. And we have highly variable overpressures in this cyclic case. And that's really what's going to control all of the patterns that we then see. So this first plot here, I'm showing the normalized event rate through time. And for constant injection, we have a ramp up of events over the first about 5 years, and then a steady decay through time. With cyclic injection, we get a large increase in events in that first set of injection. And again, that's because our overpressures are higher. And then we see a steep decline, but then we get, with each successive injection period, we get our events increasing again and decreasing. So we continue to have large numbers of events sporadically in that case. Additionally, interestingly, we found, and again, this is likely due to those higher overpressures, we get that events migrate away from the injection well faster under cyclic injection conditions, and compared to the constant injection case. Oops. And then if we look at what the pressures are at the location that an earthquake occurs, we again see that basically these events are really being driven by those high pressures at the location where the earthquake is occurring. So for the case of constant injection, we see this peak in the pressure. These are events happening close to the wells and then decaying with time. And we again see this very cyclic pattern in the hypocentral pressure for events in that cyclic injection scheme. Another relevant question is kind of whether when your first larger earthquake occurs. And in the case, when we compare cyclic versus constant injection, we see that first larger sort of magnitude 4+ event occurring earlier than for constant injection. And that's true for both of our two kind of initial stress, average and initial stress cases, the higher stress case versus the lower stress case.
Elizabeth, it's Chris again. Sorry to interrupt. On the left, the shaded areas, like the height of the shaded areas means what? I read it from
so the shaded areas are simply just showing you where the injection is. I'm just copying the injection scenario in the back, so you can kind of see when injection is taking place in the two cases. Yeah, so it's not the event rate. Sorry,
they don't mean anything necessarily. Yeah, I see.
Yeah.
Thanks.
And so we can look at also the time between magnitude 4+ events, and we have that the magnitude 4+ events are more clustered, as you might expect in the cases of the cyclic injection versus constant injection. If we look at maximum magnitude, you can see that the main difference here is in that initial stress that we have on our fault. This is similar to the previous study I showed, where your initial fault stress matters most when you're thinking about what the maximum injection across your fault might be. And then if we look at the cumulative moment, there's slightly more moment in the cyclic injection case. And cumulative number of events, maybe slightly more events, again, in the cyclic injection case compared to the constant injection, and also more magnitude 4+ events on average across all of our 2,000 runs. So all of these results, I will say, are kind of dependent on our initial setup. They're dependent on the sort of diffusivity that we have in this area. They're dependent on the fact that we have a single fault, and of course on our particular injection schedule that we tested. But in general, for this, what we didn't see is that waiting for pore pressures to dissipate kind of improved our outcomes here. And so, this was a super simple initial study. Kayla is now looking at more reasonable, I would say, injection schedules to look at, how we can maybe better tailor an injection schedule to reduce our maximum magnitudes or number of events within a sequence. But in general, again, what we're seeing is that cyclic injection, at least in this set of runs, doesn't offer any benefit relative to the constant injection schedule. All right, so in the interest of time, I'm just going to leave these conclusions up and see if there are any questions. And thanks for your attention.
Thanks a lot, Elizabeth. What a great talk. Thank you very much. I will invite people to unmute or join me in thanking Elizabeth for a great talk in whatever way they'd like to. And then, while she's catching her breath and hopefully still have some coffee, I will invite you to, use the raise hand feature at the bottom of your screen. At least it's at the bottom of my screen anyway. It looks like that. It'll help put us in an order to ask questions, have a discussion, and again, really I encourage everyone to participate. And while you are all thinking of your first question, I will ask one. And you told us the importance of the stress level, right? And so in the models, and sensible. Yep. And what about changing friction parameters? Did that have any influence? Did you get a chance to look at that?
We have not. So these were using kind of the typical friction that Kayla's used in the past for a number of her induced and just general RSQ sim runs. So we haven't played around with whether or not how much the friction parameters matter.
Right. I mean, we could.
And I assume, I assume part of what you're getting at is, if you were to change, say, your A-B values, you could see very different behavior. So yeah, no, we have not looked at that at all. Yeah, it's
impressive results all around. Yeah. Cristiano Colatini, please go ahead.
Yeah, I've got a similar question on this one that you asked, Chris. And so, yeah,